compensate the movement of target So for this one, we need a little bit tool. The first one, I need to give you a certain tool, and they call it Spherical Geometry. And that is my first time to get in touch with this topic, because before I taught this class, I never been learning this before. But here I try to make that simple, just for necessary we need. So for the spherical geometry, that means we have a triangles on the surface of a sphere, and then we're going to find out what is the relations. So here, let me make one. So this is a big circle, and another big circle on a sphere. And this is the third big circles, so each of them are the big circle. Okay, so we make here I make the three big circles, and this is the center here. You know what mean the big circles? The big circle, that means the circle has the centers right through the center of the sphere. If that is not the big circle, then that center of that circle is off the center of the sphere. Okay, so that is we define the big circle. And from each big circle, we're connecting to the center of the sphere. Then let me make connections. So there's a line here, and this is a line here, and then connecting to this line. Okay, so that's the connections. So from here, this is the triangles we try to study here. So this triangle is on the surface of the sphere, okay? And then here I want to define a few angles, and the first one is this angle. This is called the alpha, and this angle is called the beta. This angle called gamma. So right now this is in three-dimensional. So here we call it central angles, because those angles are pertaining to the center here. So that is alpha, beta, gamma. And also we have surface angles. Surface angle, let me define it in a way, is this. And look at this carefully, and this will be confusing. For this alpha is corresponding to this edge. Okay, this edge on the opposite side on the surface here we define as an A. Okay, so that is the corresponding pairs of the angles. For beta, beta corresponding is the edge is this edge here. So this edge on the opposite side of the surface, and this one is called the angle B. In a similar way, gamma corresponding to this edge, which on the opposite side, this is the angle we call the C. So ABC are called the surface angles. And to use the little bit complicated the spherical trigonometry, you need to distinguish first is the central angles from surface angles. Okay, because they play this different role in the formulas. And now I'm going to give you the necessary formulas that will be used for our class. And there's quite a full-blown formulas. I didn't go through everything. I only pick out the one we're going to use. But just for the one I'm going to use, and you see that's a little bit complicated. And let me write down the equations first. So this is called the law of cosine. And this is only small portions of the whole equations here. So here, let me write it up is this. Cosine alpha equal to cosine beta, cosine gamma plus sine alpha, sine beta, sine gamma, and cosine A. First time you spot it's very complicated. It's involving 1, 2, 3, 4 alpha, beta, gamma, A, 4 parameters in one single equation. So here that's the reason why we need to distinguish the central angles from surface. So in this equation we only have one surface angle, which is A. The other three are the central angles. So here again, for the other the central angles, beta equal to cosine gamma cosine alpha plus sine gamma sine alpha, and cosine B, and cosine gamma equal to cosine alpha cosine beta plus sine alpha sine beta cosine C. Okay, and we can have more, but the three should be good enough. And I will leave this here, and I'm going to go to our topic and put the things there and see, because we're going to refer to the formulas here. And the three will be useful, and actually I'm going to repeating utilize these equations only, and for our topics. Okay, and they have quite a few other things, but it won't be used, so I stop listing the equations here. So now for our case, here we are given is this. We are given the launching side, and the launching side we have the longitude. Longitude usually is latitude first, and longitude. So that is the latitude. This is the longitude. Okay, and also we given our target, and we have the latitude T for target, and T for target. We are given this, and then we are given the time of flight. Our calculated time of flight, and let me say that is T capital lambda. So we're going to find is this. So this is our target, and say this is the launching site at the city, and this is a target which is a city. And we know their geographical information, and here is the time of flight determined by the fuel of the missiles. Okay, so from here we want to find is what is the launching parameters like the flight path angle and azimuth. Okay, so that is the first one. Required the launch. The second one is the total range. Okay. And this launch angle, so usually is covered by 3 angles, and that means 3 powered plus the free flight and plus re-entries. And so for this question statement, usually those ones are predefined. So which means the given. Okay, so here we only looking for is actually the free flight angle here. Okay, so for this case here, how to state our province. So here, let me make one. Is this? So I'm going to draw the locations of the launching site and target, and these corner systems. So here, this is our K. I'm going to draw the IJK corner systems. Basically, this is pointing to the North Pole. Okay. And from there, say if this is the North Pole and I make one, this is the meridian, which means the longitude of the launching site here. another, this is the target. Okay, so right now I'm drawing is on the surface of the Earth, and they have a different latitude here. So basically this is the center of the Earth. Okay, so that means here we can make one. So this is equators. Not that important, but I just want to show you the things. So right now from here you can see we measure from here, and so let me. Okay, so from here can you see this pi, the bottom portion is part of the equatorial plane. Okay, so from here we can measure is this one. I'm going to draw very thick. This indicate is the latitude of the launching site. So let me give a symbol here. This one is L0. Okay. And this one is the launching site. Is the latitude of the target. So this one is LT. Okay. And for our flight path, the free flight path, we're assuming that is under the big circles. So this is our flight path. Assuming it's on the big circle. Usually on the big circle is the most time-saving path. Okay. This is not a straight line. This is a little bit curved. So let me do the curving here. Okay. And right now I'm going to form is spherical triangles on the surface. I'm going to use is from here our introductions. This triangle is formed by three intersections of the three big circles. So here this is one circle, and then the other one we can use is this one. This is a part of the longitude of the launching site, and the other one, this is a part of the longitude of the target. Right? Able to see it? Good. Okay. So right now here we're looking for is this triangle here. And for this triangle, let me mark this one. So that is the spherical triangle we're going to use. Okay, for these spherical triangles, and then from our formula, we see we also need to make the three lines that connecting the vertices of the triangle to the center here. So let me make one. So we already have 1, 2, and 3 here. So the three. The thick line basically making the, okay, so in this way that is to mimic our models here. Okay? Okay, and now I'm going to label the given informations here. So from here you can see what I need. Let me change the colors here. The first one, I want to identify the available central angles, which means corresponding to here is alpha, beta, gamma. So corresponding to here, what is the central angles? One is this one. Corresponding to this edge is this one, right? That is one of the central angles. And what is this angle? This one is equal to 90 degrees minus L. Okay? Good. You see, from here to here is 90 degrees, and from here is to L. Okay, good? Okay, and so that we fix one, and how about this one? And this angle is, if you look at here, this angle equal to 90 degrees minus LT. Okay? Good? Okay. And how about this angle? Anyone? That angle, let me draw into the plane. This angle is the angle from our launching site to target. So this angle is from here to here, and this is our flight path. So basically that is our looking for, this one. Got it? So which means this one is we're looking for is this one. That is the entire flight range. You see, because the two edge, this edge and this edge, span the range from the launching to target. Be good? Okay. And now we, on the surface, we form the surface angle here. The surface angle is this. This angle, what is this angle? This is the longitude of this line is the longitude of the launching site M0. And this is the longitude of the target, so that is the NT. So basically this is the delta N, the difference between the launching site. So this angle is delta N. Let me say the delta N is NT minus MO. Okay. We measure the launchings, we measure the delta N eastbound. Okay. But again, here if we want to consider rotation of the Earth, and during the flight of the time, the Earth also rotating. Due to the Earth rotations, and say taking the 50 minutes, then basically this angle will be a little bit larger. Will be also including because the launching is because the target has been dragged on the surface due to Earth's rotation. So basically here must be consider the rotation speed of the Earth multiply with the total time of flight. Because once we launch, and at this moment there's a delta N, of course, but during the flight, due to rotation, the target has been changing their positions, and that position has been included by this. So this is the total angle must be equal to this one. Be good? Okay. So right now we that is the things we can have, and oh, the other one is this, and this is our flight path. So basically, initially, as we launch here, this is our velocity. Basically, our velocity at the launching is tangent to that point. So azimuth is the angle measured from the North Pole to the velocity. So basically, this angle is azimuth we're looking for. Okay, so that one. Here is the symbol I use. This is beta. Okay, so basically here I just erase this one to get rid of the unnecessary information. So beta is the azimuth. That is the angle measured from the North Pole. Okay, so why not let me change the colors and central angle using green, and the other angle basically is the surface angle here. Okay, so right now you can see the one we're looking for is happened here. So the first one we're looking for is the beta. Okay, So that one we can utilize the triangles. Let me see. So right now we're looking for is the first formulation I want to come up with is beta. So beta, I'm going to look for what is beta. And we can utilize these information. So basically right now for this case, beta will be, I'm going to utilize this information. So in the kind of the similarity, I'm going to arrange beta in these positions, okay? So beta is one of the surface angle, that is the one. And then how can we formulate? From here you can see if we're looking for this angle here, and then what we're looking to arrange is the one corresponding is the one. So beta is right now we're looking for that has corresponding the edge here. The edge corresponding is this angle. So this angle we define as alpha. Got it? Again. Right now we're looking for A, and I'm going to adopt these equations. Okay. So do these things. So corresponding to there, A has corresponding edge. This edge has corresponding angle, the central angle alpha. So from here we can identify alpha. So under these situations, again, this is the beta we're looking for, and it associates this edge. This edge has the opposite, the central angle, that is this one. So in this way, alpha equal to 90 degrees minus L0. Okay? And in this way, the other two angles are the other two. So simply it's 90 degrees minus LT, and this one is lambda. So we do this kind of correspondence, then quickly we can put into equations. Okay, so therefore, if I plug in there, and so cosine and 90 degrees minus LT equal to cosine 90 degrees minus LO cosine gamma plus sine L. Okay, so therefore from here we can have the cosine beta equal to cosine L0 sine and sine minus sine L0 cosine. So from these equations we can determine beta. However, to determine beta, we need to know the gamma here. Okay, so gamma is this. We can utilize what is gamma. So again, utilize this equation one more time. Gamma is one of the central angles. Again, I'm going to use this equation one more time. So corresponding, let me assign the gamma equal to alpha. Then the other two would be 90 degrees minus L0, and the other one is the 90 degrees minus LT. Okay, and under these situations, alpha, again, alpha is the central angle have corresponding edge, and that is A. So here we have this lambda here. Lambda here looking for have corresponding edge is this edge. This edge has corresponding the surface angle here, and that is theta n plus omega. Are we good? One more time. Using these equations, we have designated lambda and alpha. So alpha corresponding is this edge. This edge corresponding is the surface angle. So the same thing here. This lambda has corresponding edge. This edge corresponding to this surface angle. So that is this angle here. Be good? So using that equation quickly, then we can determine the cosine lambda equal to sine LT sine L0 plus cosine LT cosine L0 and cosine theta n plus. So using these equations, you use equation 2 to determine lambda, and then use equation 1 and to determine beta. So that is the sequence. You solve for the lambda first, and then plug into here, you solve for beta. And the effect of the Earth's rotation appeared here. Be good? So these sections is very kind of combining the everything we have. And again, these sections won't be covered in the final test, but I'm considering including these sections in my next teaching 2 years later on. From here, before I move on to kind of further discussions, any questions about the two equations? So here again, we simply, based upon this geometry, simple, not simple, a little bit complicated geometry, and I repeated using the first equations and carefully assign the pairs of the parameters and for the two equations.